In this video, we're going to solve applications involving exponential modeling. Have your scientific calculator ready. We're going to need it. This is from Unit 9C. And before we get started, we're going to need to talk about something new called a logarithm. We're going to use logarithms to help us solve exponential equations. We use exponentials to help us solve logarithmic equations if we run into those. And let's just kind of show you how this is going to work. If y equals a to the x, then I can take the log of both sides like this. And then one of the fun things that happens with logs because of their properties is that the exponent is going to come down in front of the log by way of multiplication like this. And then I can divide both sides by the log of the base. And I can solve for the exponent like so. Now, it really doesn't matter. I used log base 10 here. I could have also done this with log base e, which is written as ln. And usually math people prefer ln just because it's one less letter to write. And we'll come out with exactly the same answer whether we use log base 10, which is right here on your calculator. You see that the inverse of that is 10 to the x, or whether we use the natural log, ln, and the inverse of that is e to the x. But those are the two bases that our calculator for sure understands. And if you have smarter calculators, such as this one that I have, my TI-84, you can choose any base that you want to. That's not loading for me right now, though, so I'll go ahead and close that up and reload it later and show you. So let me go ahead and clear all this and start working on problem number 1. And then we'll also show you how you can solve this problem graphically in just a second with either graphing calculator or with something like Desmos. So let's write our equation here that our population P is equal to our initial value of 1500 times 1 plus our r. Well, our r is negative 1%. So that's 1 minus 0.01. That's going to be raised to the t power. So P is equal to 1500 times 0.99 raised to the t power. I'm interested specifically in when this population of this endangered animal is going to reach an extinction level of 70 of them. So I'm going to set this equal to 70. It's equal to 1500 times 0.99 to the t. 70 divided by 1500. Let's see if that comes out nicely here. It does not. So let's just change that to a fraction. It's going to be 7 over 150 is equal to 0.99 t. And we can choose any type of log that we want to. Let's use ln. So ln of 7 over 150 is equal to ln of 0.99 t. So switch sides here. T times ln of 0.99 is equal to ln of 7 over 150. If you know some log properties here, you could also write this right-hand side as ln of 7 minus ln of 150. It's the same thing, but it really doesn't matter. I'm going to keep it as a single log there for the purposes of typing it into my calculator. Ln of 0.99 divided by ln of 0.99. T is going to be equal to, I'm going to show you here that this is going to be ln of 7 over 150 in the numerator and ln of 0.99 in the denominator. And we get 304.9375851 approximately. So this is not an exact answer because, like square roots, most of the time logs are non-repeating, non-terminating decimals. And so we're going to say that this is about 305 years. 305. We'll move around to the nearest whole number as needed. We're going to say that the model is valid because the population, the initial population is not very high at this rate of decaying, the number of years predicted by the model is reasonable. And the reason we're saying, talking about it not being very high is 305 years in terms of the lifespan of a species is not very long. So, we're thinking about things that maybe, if there wasn't the poaching going on here, they could be living for thousands, maybe even millions of years, something like that, if they had enough food, enough shelter, didn't have invasive predators, all those types of things, didn't have poachers. So in just a few hundred years here, just because of the poaching that's going on with this creature, it's going to reach an extinction level event if something doesn't happen. So that's why this is the type of reason why we have anti-poaching laws, to keep creatures from, species from going extinct like this. And it doesn't have to reach a level of 0 to be considered extinct. It just has to reach a level where there's not enough genetic variation anymore to be able to successfully weed out these birth defects that would be fatal and things like that. There's so much inbreeding that the negative traits wouldn't be able to be bred out, and it's going to eventually die off because of that. So, all right, let's look at number 2. The drug Valium is eliminated from the bloodstream exponential decay, with a half-life of 36 hours. That means that every 36 hours, half of the drug that was in the system before is there now. So we're going to have the Q function here. Q is equal to, suppose that the patient receives an initial dose of 20 milligrams, and then we're cutting it in half. So this is going to be 1 minus 0.5. So that's going to be 0.5. And let's see, every 36 hours, it cuts in half. So the easiest way to write this is t divided by 36 to see how many cycles it's gone through to cut in half like that. So when they tell you that something like half-life and then tell you what the half-life is, then this is t divided by big T, where T is the half-life, and the half-life is 36. So let me write that formula up here. Q equals Q naught times 1/2 or 0.5 raised to the little t, which is my variable, divided by big T, which is my half-life. All right, and we want to know how much Valium is in the patient's blood at noon on the first day, and they received the this is received at midnight, so this is at 0-100 hours, so 12 hours later. We want 20 times 0.5 raised to the 12 over 36. And so we should have Q is, and they want this answered to the nearest tenth of a milligram. So this is 15.9 milligrams. Q of 12 is equal to 20 times 0.5, 12 over 36. It's approximately 15.9 milligrams, right? 15.9. And then estimate when the Valium concentration will reach 30% of its initial level. So we want that this Q over Q naught here, we want that to be 30%. So 0.30, we want that to be 0.5 to the T over 36, like that. We've done this division here to find the percentage of what's remaining. We converted that percentage to a decimal here, and have what's left on the right-hand side of the equation. We're going to use a log here. We used ln last time. Let's use log this time. Really doesn't matter. 0.30 is equal to log of 0.5 to the t over 36. That exponent is going to come down front. T over 36 times log of 0.5 is equal to log of 0.30. And so t over 36 is equal to log of 0.30 over log of 0.5. And then we're going to multiply by 36 to solve for t. 36 log of 0.30 over log of 0.5. So 36, let's just put the fraction in there first. 36 times the log of 0.30. Calculator understands multiplication there. If I put a number next to the log symbol, and then log of 0.5, and t is going to be equal to 62.5 something. We want to round up to a whole number of hours. So it's about 63 hours later. And you kind of get the idea now that stuff probably stays in your system a whole lot longer than you think it does. So there's still 30% of the dose in your system after 63 hours. And this is one of the things that we're probably going to talk about. Nope, we don't have a question on it, but one of the applications that's in this section that's really important is to figure out BAC, blood alcohol content, and it's an exponential decay as well, and to figure out how long somebody needs to wait after so many drinks to be below the legal limit and be able to drive. And you'll see when you do those problems that it takes a lot longer for alcohol to be eliminated from your system than you may think. And it has to do with the total amount that's present and things like that. So it's very different if you drink one drink and then wait another hour and drink another drink than if you drink two drinks in quick succession and then you have a much larger initial value. And so anyways, there's you can do some of those problems and investigate that if you would like to. A toxic radioactive substance with a density of 7 milligrams per square centimeter is detected in the ventilating ducts of a nuclear processing building that was used 45 years ago. It has a half-life, the half-life of the substance is 20 years. What was the density of the substance when it was deposited 45 years ago? So Q of 45 is equal to 7. We want to know Q of 0 is equal to what? We have the model that Q at time t is equal to Q at time 0 times, and now this is going to be 1 minus, well, this says half-life, so this is going to be 1/2 to the little t over, and then big T here for the half-life is 20 years. So we're going to make a substitution here, and we're going to say that 7 equals Q naught 0.5 raised to the 45 divided by 20. And so 7 over 0.5 to the 45 divided by 20 is equal to Q naught. So let's use our calculator for that. 7 over 0.5 raised to the 45 divided by 20 is Q naught is 33.3 milligrams per square centimeter. We were told to round to the nearest tenth as needed. In 2000, the median home price in a certain city was about $290,000. And from 2000 to 2006, home prices in the city rose at an average rate of about 11.6% per year. Erase this. So our P naught, our initial price here is $290,000. Our R value here is going to be 11.6%. So we want P of T is equal to 290,000 times 1.116 to the T, where T is equal to the number of years since the year 2000. So we want to find an estimate here of what's going to happen in 2020, which is 20 years after the year 2000. 290,000 times 1.116 to the 20th power is 290,000 times 1.116 raised to the 20th power is 260,445 point 31. This is in dollars, but we're not asked to answer in dollars. We're asked to answer in millions of dollars. In 2020, and round to 2 decimal places is needed. So this is going to be $2.60 million. Well, is the expected median home price. The actual median home price is far less than the median home price calculated using the 11.6% growth rate. That growth rate was not constant over this period of time. So we have grossly overestimated the median home value using this model, because we assumed a constant rate of growth when that wasn't the case. The market goes up and down and fluctuates quite a bit. So this was not a good model. All right, that's it for this video. And that's actually it for all of our topics for Math 154. So after this, most of you will be taking Math 245, Statistics 1. I'll be working on some videos for that in the near future. So keep an eye out for those videos, and I'll see you back here for that. Good luck.